Hello everyone, I hope you are doing great. So today we are talking about equation-based modeling in COMSOL Mod Physics. So what is the equation-based modeling and why it needs us? So as you know, most people use predefined interfaces like heat transfer, AC/DC, electric currents, acoustics or optics, or just the semiconductors, or all others that we already know them. But all that predefined interfaces based on just differential equations. So COMSOL calculates them based on that equations. They are just a particular view, each of them. But sometimes we cannot find the correct equation as we need. So that time it will be a problem if we just use the other equation for our modeling. To get the successful result as the experiment, we have to specify our own equation. So that time the mathematics interface can help us. Okay, while you choosing the physics, so there is a mathematics interface. Under them there are a lot of equations. For example, there is PDE interface. Under them there are different kind of PDE equations. That means a partial differential equation, by the way. And they are also partial differential equations, so you can use them if you are modeling based on the PDE. And there is a ODE interface, that means ordinary differential equations. So there are different types of them, and also there are so on, because you have to choose your own equation and it should be really properly to your project. So you have to use that equations. And there is also, I have to tell it, there is also classical PDEs. That means these equations uses frequently. So that is COMSOL. That's why COMSOL just separated from other PDEs. For example, there is a Laplace equation, Poisson's equation, heat equation, or Helmholtz equation. They are also just the interfaces like these predefined ones, but the difference between them, for example, the heat equation is the same with the heat transfer in solids. But this is just the equation. We cannot change the equation. We can just specify the boundaries or surface, or just change the material coefficients like that. But in that heat equation, we can change the first coefficients, the general view of the equation, and we can also specify for the coefficients just one function. So it means it will be more complex than predefined interfaces, but it can help us to reach successful result. So let me show you the difference between heat equation and heat transfer in solids. As you see, there is a temperature, I mean the heat transfer in solids interface. There is a dependent variable is temperature. So the equation based on to the temperature changing, and in the heat equation there is a given U, but as you see the dependent variable unit is the Kelvin. So it means it's also temperature. It should be also temperature. It must. So we can change it as T, and we can start study. So we are just comparing two interfaces to learn. So that's why we can choose just stationary study right now. Okay. So let me just create a block to see the heat transfer. It should be 2 blocks, I think. It doesn't matter, it depends on your project. I'm just showing for an example. So let me change the Z direction, Z position, and it will be 2 blocks together. And let me choose a material. So it should be the material that heat should transfer easily. So I think it will be metal, any kind of aluminum or iron, just like let me choose iron. 2 blocks. I chose the material iron, and I don't pay attention for now that heat equation, because let me just see the result of heat transfer in solids. So there is given a reference temperature 293.15 Kelvin. So as you know, we don't need to change anything because it's already predefined. So there is an equation, as I said before. So this is a differential equation. This is an operator, and it can help to calculate the heat in that blocks, the transfer in that blocks. So let me just change the boundary condition. So I just choose the temperature for 2 sides. Let me choose the upside and the downside. 1 should be 0. 1 should be, let me change it, 400 Kelvin. Okay, and mesh should, let me choose a physical controlled mesh, and when I come to study, I didn't pay attention to the heat equation. That's why I just turned it off and click the compute. And it can help, it can show us a result of heat transfer in solids physics. Okay, this is the result. So this yellowish color means the 400 Kelvin, and the other side is 0 Kelvin. So let me show you the maximum and minimum values of that temperature. Here, the maximum value of 400, that surface, and the minimum value is that surface. As we just said, the boundary condition is like that. Okay. Then let me set my heat equation as a heat transfer in solids. So this is my general view of heat equation. So we just change the dependent variable T. That's why there is a T, capital T. That means the temperature. This is a left side, and left side there is each term there is a T. That means the temperature. So there is a unit of them. So if we don't need the temperature, and we have to change that equation U to other equation, so we can also do it. But right now I don't need it. I just want to show you the result in comparison with the heat transfer, and that's why By the way, you can told me how can we change the coefficient. So there is a given coefficient that is diffusion coefficient C. There, if we change this term as a 0, that means these all term will be the 0, because C times any value will be equals to 0. So it depends on you. If you just write the one function like exponential or a square t or square function, it doesn't matter. Console can get it. It depends on your model and your equation. So in the heat transfer equation, we need just these equations. That's already automatically defined. So we don't need to change any of them. Because if you change one of them, it won't be the same result with the heat transfer in Solis. It should be the same equation as this one. Okay, you can see here dA is a 1, so it means dt by d little t plus, okay, let me show you the, okay, sorry. Let me write you the view of that equation. So dA is a 1, that means dt by d little t small t, sorry, plus nabla times minus nabla t equals to 1. This is the heat equation here. Okay. Then there is given the meaning of the nabla operator, that is a derivative of that variable. And there is given the initial values. As you know, there is 293 and 15 Kelvin, so I have to just specify it, and the one-time derivation of that value is 0. We don't need to change it. And here we just set the boundary conditions. I mean just the exact value of that dependent variable. So we can do that thing with PD equations or just any kind of equation-based modeling. To do that, we can use Dirichlet boundary conditions. This is the same. This is uses for the same purpose. So I have to just specify it for the 400 Kelvin. And the other side should be the 0. Okay. Yes, this one, 0. And this is ready. So we just, let me add another study for not confusing. Add another study. And here I just turned off the heat transfer in Solis because we already see it. So we need just heat equation here. And I just compute it again. And here the result. So here my last result, that is given by heat transfer in Solis, and this is the our new result used by equation-based modeling. So to do the similar like last one, I just delete the slices and just add the value. and it uses, I think, heat heat camera light color table. So I just want to change it camera light. Okay, and we just specified last time maximum and minimum values. Okay, you can see here this is our new result. So this surface is a maximum 100 Kelvin, and that surface is a minimum what -1, where I did wrong. Let me just okay. This surface is a minimum 0 Kelvin, and that surface is 400 Kelvin. So this is the same result that we got the last time. There is no difference between them, but one of them is used by using heat transfer in solids interface, that we cannot change the equation view here, but one of them is used just differential equations that we said already by changing the coefficients. So if you know equation-based modeling, it's your good side. So you can define any open interface yourself, and it will be so easier to understand what's going on that model project. So I just recommend to learn that in equation-based modeling. But yeah, if you have any kind of issues with mathematics modeling, so you can use also predefined interfaces. They are also the same as I said before. So for now, that's all. And the next lesson, it will be to continue that video lesson. So I just want to show you that heat equation while using PDE. Just not using the classic equation, just using the whole PDE equation. So don't ignore us and like our videos. Thank you.